Greetings, everybody. Learning is a hobby here. I'm going to do my summary for chapter 30 in Spivak's calculus book here in this video. This is the last chapter in the epilogue, and there is an exercise set for this. So the next video after this one will be my solutions to the exercise set for chapter 30. There is no exercise video for the exercise set for chapter 29 because, as I mentioned at the end of the video for my chapter summary for chapter 29, there are only two questions in that chapter, and we've done the first one in Tau, so I'm not going to do it again. And the second one we're going to do in Tau eventually, so I'm not going to do it here in Spivak. So let's get to my notes, and we'll summarize chapter 30. Okay, this is the last thing that we need to do for our construction of the real numbers. Let me just move things around here. Okay. So in this chapter, we're going to show that the real numbers are up to isomorphism, the only complete ordered field. In chapter 29, we show that there is a complete ordered field, namely the real numbers, and we constructed them using Dedekind cuts. Now we're going to show that they're the only complete ordered field up to isomorphism. I've done an example with an isomorphism in chapter 28 in the summary. So if you've seen that, then maybe you're familiar with it. Or if you've taken, algebra, then you might be familiar with the concept of isomorphism as well. So let me just start with the at the beginning here. So we'll now revert to the usual notation and way of thinking about the real numbers. So in other words, we're no longer going to think of them as cuts. We're not going to think of them as sets of rational numbers. Just think of them like you usually do. All right. In this chapter, we're interested in one question. Are there any other complete ordered fields other than R? If taken literally, then the answer is yes. For example, the field F3 from chapter 28 is a complete ordered field. However, as I showed, when I say I mean me, not Spivak, I showed that through constructing an isomorphism, I showed it in my video for chapter 28 that F3 was isomorphic to the real numbers. But he says that here too. F3 is, in a sense, simply a renaming of the elements of R. This shows that any intelligent consideration of this question requires some mathematical means of discussing such renaming procedures. In order to do this, we need a much more general conception of a function. So here's the more general definition. And we've seen this definition already, but uh, maybe not in Spivak. So, a function is a collection of ordered pairs of objects of any sort, which does not contain two distinct pairs with the same first element. Excuse me. The domain of a function f is the set A of all objects A, such that A comma B is an f for some B. This unique B is denoted by f of A. If f of A is the set B for all A in A, then f is called a function from A to B. And he gives some examples here. F of x equals sine x for all x in R. And f is defined only for the real numbers. We'll see why he's saying that in a second. Then f from R to R is, the sine function is a function from the real numbers to the real numbers. It's also a function from R to the closed interval from -1 to 1. Right? He gives a bunch of examples here, so I'm not going to belabor them. I'll just say, f of z equals sine of z for where z is a complex number, then f is a function from the complex numbers to the complex numbers. Example C, the complex valued function f of z equals e to the z. It's also a function from the complex numbers to the set of all non-zero complex numbers. Part D, he has the argument function modulo 2 pi. So theta is a function from the set of complex numbers that are non-zero to the set of real numbers between 0 and 2 pi. And then example E is the function that actually I defined, which was the isomorphism, that I created in chapter 28. So I won't talk about this again, but these are all examples of that type of function. Like I said, we've actually looked at things like that in Tau already, but I don't remember really talking too much about that in Spivak, so maybe he hasn't talked about that yet. It's been a while since I went through chapter 1 and through chapter 8 in Spivak, so I don't remember everything that we did. But anyway, here's a definition. So really, this chapter is really one definition and one theorem. But well, you'll see it in a second. So here's the big definition. If F1 and F2 are fields, an isomorphism from F1 to F2 is a function f from F1 to F2 with the following properties. So f is 1 to 1, meaning if f of x is not y, then f of x is not f of y. F is onto, so in other words, if z is in F2, then z equals f of x for some x in F1. If x, y is in f, then f of x plus y equals f of x plus f of y, and f of x times y is equal to f of x times f of y. This property here shows that f is something called a ring homomorphism. What that means is that the function f preserves the algebraic structure of the underlying field. Right? And if F1 and F2 are ordered fields, we also require that if X is less than Y, then f of X is less than f of Y. So in other words, F not only has to be a ring homomorphism, it also has to preserve the order properties of the underlying field. Okay, a note, F1 and F2 are said to be isomorphic if there's an isomorphism between them. And then here's the big theorem. So the rest of the chapter is going through this theorem. Now it's only one proof, but the proof is very long. So just bear with me. Okay. So here's the theorem. If F is a complete ordered field, then F is isomorphic to R. So what we're going to do to prove this is we're going to actually construct an isomorphism. But in order to do that, we have to show a whole bunch of things. Um, which is what Tao does in the book. I'm following Tao's proof here, so I'm doing the construction the way that he does it in the book. But the way that sorry, I keep saying Tao. The way that Spivak does it in the book, uh, it's very bare bones. He hardly proves anything. He kind of just says things and then sort of gives the reader, a guide to like, you can do this to show this or things like that. So I filled in all of the details in my proof here. So my proof here is actually a little bit longer than Spivak's because he doesn't do the details. So, but here we go. So part one, define f on the integers as follows. So we'll define f of 0 to be 0. We'll define f of n to be the sum of the multiplicative identity in the other field f summed with itself n times for n positive, and the negative of n summed with its one summed with itself absolute value n times for n less than 0. Here, the number 1 here is not necessarily the real number 1 or the integer 1. It stands for the whatever the multiplicative identity is in the field f. Right, that it's easy to check that f of m plus n equals f of m plus f of n, and f of m times n equals f of m times f of n for all integers m and n. And then Spivak says it's convenient to denote f of n by bold-faced n, little n. Now here, this is all Spivak says. He just says it's easy to show that. He doesn't show it. So I actually have the proof here that I wrote out. So f of m plus n is 1 summed with itself m plus n times. And since f is a field, it had the addition satisfies the associative law. So we can reassociate the sum of 1's m plus n times into a sum of 1 m times plus the sum of 1 n times. Um, so f of m plus n equals f of m plus f of n. And a similar thing, for the product. So f of m times n is f of the sum of n with itself m times, which is equal to f of n, added to itself m times in the field f, which f is a field, so it has the distributive law. So you can factor out the f of n. So you get 1 added to itself m times multiplied by f of n. So f of mn equals f of m times f of n. All right, so that's the proof. Next, we define f on the rationals by f of m over n equals m over n. Um, this should actually, because he uses boldface for the elements of the field f. I should probably, because I didn't write it boldface, I should probably just write it like this: f of m. F of m over or actually, we don't know if there's this concept of division here, so I'll just write it as a multiplicative inverse. So equals f of m times f of n inverse. All right. Notice that 1 added to itself a bunch of times is not 0 if n is greater than 0, since f is an ordered field. All right. And now we have to show that f is well defined on the rationals with the way that we defined it, because remember that rationals are equivalence classes of ratios of integers. So let mn k over L be rational such that m over n equals k over L. That means ml equals k times n. So f of ml equals f of kn, which implies f of m times f of L equals f of k times f of n, which implies that f of m times f n inverse equals f of k times f of L inverse. Also, ln not 0 implies f of L, f of n not 0 by 1. Okay, so that checks out. Then B, if R1, R2 are rational, then we have to show that f of R1 plus R2 is f of R1 plus f of R2, and f of R1 R2 equals f of R1 times f of R2. And this follows from just the way that we defined the operations here. So I won't belabor this. You can look at the details. It works the way that you think it would work, right? And using the fact that F is a complete ordered field. Okay, part C, R1, R2, and Q, then R1 less than R2 implies F of R1 less than F of R2. So in other words, for rationals, at least the F preserves the order relation. So R1 less than R2, implies there are integers P, Q, S with S greater than 0. P less than Q, and R1 equals P over S, R2 equals Q over S, then Q is P plus N for some natural number N, and F of Q equals F of P plus N, which is equal to F of P plus F of N by, what we said previously. And notice that's greater than F of P. We know that because F is an ordered field, right? Then F of P times F of S inverse is less than F of Q times F of S inverse, which implies that F of R is less than F of 2. Sorry, f of R1 is less than f of R2. Okay. We need a quick definition here. For any x in R, let AX be the set of all f of R in F, such that R is a rational number and R is less than x. Then we have this proposition, A sub x is not empty and AX is bounded above. So here's my proof. Again, Tao doesn't prove any of this stuff. He just states it. Sorry, I keep saying Tao, Spivak. I still haven't gotten over the 5 chapters we did in Tao so far, I guess. Anyway, Spivak doesn't prove any of these things. He just says it. So here's my proof that this is true. If x is a real number, then there's some r in Q, r less than x. So a sub x is not empty. If y is a rational number with y greater than x, then y greater than r for all r less than x implies f of y greater than f of r for all r less than x, so A sub x is bounded above. And since f is a complete ordered field, sup of AX exists, and we define f of x to be equal to the supremum of the set AX for each x in R. All right, a note here. We need to show that if x is rational, f of x equals f of p times f of q inverse equals supremum AX. In other words, we need to show that the function f is well defined not only over the rationals but over the way we defined it for real numbers as well. This depends on the completeness of f, so we'll see that in my proof in a second. So here's the proposition: the elements n equals 1 plus 1, et cetera, are in f form a set which is not bounded above. We're going to need this to prove that the function is well defined in a second. So here's my proof of that. Let A equal the set of all such numbers in F. Then A is a subset of F and A is not empty. Assume A is bounded above. Excuse me. Then since F is complete, A has a least upper bound. Call it X hat, which we're defining to be supremum A. For all N in A, n is less than or equal to x hat. In particular, n plus 1 is less than or equal to x hat, which implies n is less than or equal to x hat minus 1. Since n was chosen arbitrarily, n is less than or equal to x hat for all n in A. Sorry, this should be less than or equal to x minus 1. Let me fix that. Hang on. So minus 1 for all n in A. This contradicts that x hat is the supremum of A. Therefore, A is not bounded above. Okay. Another note here, the consequences for n not being bounded above in R have similar consequences in F. In particular, this property star holds if A, B are elements of F with A less than B, then there's a rational number R such that A less than F of R less than B. Uh, and I'm just saying here, this is one of the consequences that are mentioned above. Okay, and now we can get to this proposition. F is well defined on the real numbers. So here's our proof. If y is a rational number with y less than x, then f of y less than f of x. So f of y is in the set A sub x, which implies that f of y less than f of x. Then f of x is an upper bound for ax, so supremum ax less than or equal to f of x. And then we have to show that the supremum is actually equal to f of x, so we'll do this by contradiction. If sup of ax is less than f of x, then there's a rational r such that sup of ax is less than f of r is less than f of x by the property star up above that we talked about. Then r less than x implies f of r is an element of ax, which implies that f of r is less than or equal to supremum ax, and this is a contradiction. Therefore, supremum ax is equal to f of x. Right, so the f is well defined on the real numbers. So in other words, the way that we defined f with respect to rational inputs matches with our definition of f where it takes real inputs. Okay, another proposition from f from R to f is an isomorphism. So this is what we want to show. And there's remember in the definition of isomorphism, sorry, let me take a drink of water here. In our definition for isomorphism, there were four conditions. So we're going to prove them all, but in slightly out of order. So we'll prove number 4 first. So we want to show that F preserves the order relation. Okay, let x, y be real numbers with x less than y. Then the set AX is a subset of A sub y, and sup AX is less than or equal to sup AY. Also, x less than y implies there are RS rational, such that x less than R less than S less than y, which implies that the supremum of AX, which we define to be f of x, is less than or equal to f of R, which is strictly less than f of S, which is less than or equal to f of y, which we define to be the supremum of AY. Okay, so the order relation is preserved. Then we go on to property number 1. So we want to show that f is f is 1 to 1. Let xy be a real number, then x not y. Let xy a real number such that x is not y. Then x less than y or y less than or y greater than x. In either case, f of x greater than f of y, or f of y greater than f of x by property number 4 that we just proved, which implies that f of x is not f of y. All right, property number 2, we have to show that f is onto. Let A be an element of f and B be defined to be the set of all rationals R and Q, such that f of R is less than A. Then B is not empty, and there's a rational S with f of S greater than A, which implies that f of S is greater than f of R for all R and B, which implies that S greater than R for all R and B, which implies that B is bounded above. So X equals supremum B exists in R because remember, we showed that R is a complete ordered field. Either f of x less than a or f of x greater than a or f of x equals a by trichotomy. Since f is an ordered field, assume f of x is less than a. We're going to do this by contradiction. Then there is R in Q with f of x less than f of r less than a, which implies that r is an element of B, and x less than r, which contradicts that x is the supremum of B. Next, we assume that f of x is greater than a, so we have a contradiction there, right? F of x, assuming is greater than a, then again, there is R in Q such that f of x greater than f of r greater than a. That implies that x is greater than r, which implies r is an element of B. but R greater than Y for all Y and B. This is also a contradiction since R is an ordered field. Therefore, f of x has to be equal to A. That's all that's left from the trichotomy property. All right, property number three, we have to show that F is a ring homomorphism. So let x, y be real numbers. Assume that f of x plus y is less than, again, this is contradiction, f of x plus y is less than f of x plus f of y. Then there is a rational R such that f of x plus y less than f of r less than f of x plus f of y. Then x plus y is less than r. We can write R equals R1 plus R2, where R1, R2 rational, such that x less than R1, y less than R2. Then f of r equals f of R1 plus R2 equals f of R1 plus f of R2 greater than f of x plus f of y, which contradicts that f of r is less than f of x plus f of y. Okay, so maybe it's the other thing. Assume f of x plus y greater than f of x plus f of y. Then there's, again, a rational R with f of x plus y greater than f of r greater than f of x plus f of y. Then x plus y greater than r implies r equals r1 plus r2 for r1, r2 rational, and r1 less than x, r2 less than y. Then f of r equals f of r1 plus r2 equals f of r1 plus f of r2, which is less than f of x plus f of y, which contradicts that f of r is greater than f of x plus f of y. Therefore, the only thing left by trichotomy is that the two things are equal. So that shows that f of x plus y is equal to f of x plus f of y. And we have to show the same thing for holds for multiplication. And it's done in exactly the same way. Again, Spivak doesn't prove it, so I'm filling in all the details here. So this is the proof, and it's very similar to the one that we just did. So next, assume f of x, y is less than f of x times f of y. Then again, there's a rational r with fxy less than fr less than fx fy, which implies xy less than r. And that implies that r is r1, r2 with r1, r2 rational such that x is less than r1, y is less than r2. F of r equals f of r1, r2 equals f of r1 times f of r2. By the way, we defined f over the rationals. And notice that that's greater than f of x times f of y, which is a contradiction. And then if you show the other, if you assume the other way, you get a similar contradiction. I won't go over it in detail. You can pause your screen here and see it. It's the same exact thing. And that's another contradiction. Therefore, the only thing left by trichotomy is that f of x, y equals f of x times f of y. Therefore, f is a ring homomorphism. Okay, and that's it. That shows that uh, we have an isomorphism between the real numbers and the complete ordered field F, which means up to isomorphism, there is only one complete ordered field, and it's any such thing as isomorphic to the real numbers. Okay, so we've now shown that there's a complete ordered field, and oh, I just said that. So that's it. That's chapter 30. Let me stop my screen share for a second. There is still an exercise set for me to do. There's like 5 questions, so I'm going to work on those tomorrow probably. So I might be able to get that video actually published to YouTube this weekend because they don't look like they're that difficult, the problems. And then finally, we'll be done with the epilogue and we can actually get into derivatives and integrals in Spivak. So we're going to go back to chapter 9. All right, guys, I'm going to end the video here. I'll see you in the next one. Let me know what you think down below, et cetera, et cetera. Give me a like and subscribe. Check out the Patreon page, et cetera. I'll see you, all right, I'll see you guys in the next one.